Jnanam paramam dheyam. Knowledge is supreme.
So we have looked at three different ways in which the dynamic model can be represented, can be formulated. So let us now look at how we would be representing it so that it can be helped to understand the dynamics or design a control system using that particular dynamic model. So one of the most commonly used way of analyzing process dynamics and also designing control system is known as a transfer function model. So far any dynamic model, what it tells me is how does the output change as a function of input, as a response to input, as a function of time. And in transfer function model we actually move from time domain to what is known as a Laplace domain. And this is a very old way of analyzing process systems, and the whole philosophy behind that is back in, let us say, 1920s, 30s, about 70, 80 years ago, the computing power of computers was very limited, and in that case we have seen that these dynamic models which we have generated, let us say for an example the first principle model, these are ordinary differential equations. So using those to predict the response of input on the output, you have to solve them numerically because most of the time analytical solution might not be available, and in that case doing that repeated times becomes a very difficult job manually, and the computers were also not that powerful like the ones which we have today. So in that case the researchers wanted to come up with an elegant way of analyzing these systems without directly solving them in time, and the nice breakthrough which they got was transferring the whole analysis from time domain to a Laplace domain, a complex Laplace domain, and the major advantage or rationale behind this was, if we have a ordinary differential equation in a time domain, when I convert it into a Laplace domain, it actually gives me an algebraic equation. So if it is a derivative of a function, then what you get is an algebraic equation. So ordinary differential equation gets converted into an algebraic equation, which are easy to analyze, and we will see this as we go into this course, that having analysis in the Laplace domain has very significant advantages compared to working with the time domain. Even though nowadays our computing power is very advanced and we can simply solve these ordinary differential equations quickly, still the insights which we get by doing the analysis in Laplace domain are still more insightful than just doing a numerical analysis in a time domain. So what we do is, we have this relationship in time domain, we just convert it into a Laplace domain, and what we get is a Laplace transform of output, Laplace transform of input, and a factor or a functional in S which kind of sorts of a multiplying or transfers the effect of input into the output. This is known as a transfer function. So you can write transfer function for the process as Ys over Us. So it transfers the effect of input on the output in Laplace domain, and we will see that the form of this transfer function will give us lot of insights about the process dynamics, as well as we will be using this particular transfer function model for designing a control system. The advantage of using transfer function model is that it simplifies the analysis by converting a differential equation into an algebraic equation, The major limitation of transfer function based analysis is that we can use Laplace transforms only for linear functions. So, as long as the relationship between input and output is linear, we can use the Laplace analysis, and we would see that especially when the processes are nonlinear, which is quite common for chemical engineering systems, we would try to see how we can get over this requirement of linearity by linearizing a nonlinear function. So, when we talk about a nonlinear process, that time we will touch upon this aspect of how do we still use Laplace based analysis when the process is nonlinear. So, we will close out this first lecture with the final topic on the analysis of degrees of freedom of a process. So, we saw that control system is implemented to satisfy a certain objective on a process. So, the natural question is, how many objectives can I satisfy in a given system? Is there any maximum limit on that? And we can easily guess that we cannot indefinitely keep on satisfying multiple objectives for a process. There will always be some maximum limit on the number of objectives which can be satisfied, and that will be given by what is known as an operational degree of freedom analysis. So, we know what is the degree of freedom for any system. So, degree of freedom is how many handles do we have in that system, or how many independent specifications we can make in that system without compromising the final outcome of the process. So, degree of freedom represented as DOF is generally given by a difference between number of variables minus number of equations. To drive this point, let me take a very simple example. If I say that I have two variables x and y, and the only information I have is the addition of them gives me 100, and I ask you how many different ways in which I can choose x and y, and then there will be infinite ways in which I can choose x and y. But if I say that x is 10, or I make one specification, then automatically the values which y can take, there is only a single value which is 90. So, this particular system has one degree of freedom. So, if I specify one variable, then the system is completely defined. And if we use the same formula of degree of freedom, we have number of variables. In this case, there are two variables, and a number of equation, there is only one equation. So, I have one degree of freedom. So, we will be using a similar concept to find out what is the degree of freedom of a dynamic model of a process, because that is what is eventually going to give rise to process control. So, let us look at an example of stirred tank, and here we are saying that there is some input and some output in this process. You have some level in the tank, and then we have written the dynamic equation for this as A dH over dt is equal to F in minus F out. Now, for this particular system, we have three variables. So, this is variable number 1, this is variable number 2, this is variable number 3, and then we have only one equation. So, the degree of freedom is 3 minus 1 is equal to 2. So, there are two independent specifications we can make, which are either F in and F out. As long as we specify F in and F out, the rest of the system will get specified. So, now let us look at what are the different values a degree of freedom can generally take. So, degree of freedom can take various values for any system. Let us say if degree of freedom is less than 0. So, if degree of freedom is less than 0, that means I have more equations than unknowns. So, these systems will be mostly practically impossible. Degree of freedom may take a value of 0, which means number of variables equal to number of equations, and this is a completely deterministic case. So, we can just solve this system of equations and get a solution. There is no degree of freedom, or there is no way to manipulate this particular process. And then lastly, the degree of freedom can take values greater than 0, which means number of variables is more than number of equations, so that some of these variables can be selected by us, and then we can finally arrive at the case where number of equations is equal to number of variables. So, there is a freedom to choose few variables, which we also call as there are few ways to manipulate the process. So, these will be the processes which are manipulable, these will be the process which will be relevant from the control point of view, because this case definitely is practically impossible. This case tells me that there is no way for me to manipulate the process. So, only these cases are the ones where the process can be manipulated, and we know from control that we have to be able to manipulate the process. So, degree of freedom greater than 0 is a requirement when we talk about any process control. So, if we come back to this example, we have degree of freedom 2, so that means this process can be controlled. And the next thing which we want to look at is what would happen when we have a process control. So, process control system reduces degree of freedom. So, let us look at the previous example of stirred tank, and in this case let us look at we talk about a feedback control strategy. So, in feedback control strategy we would measure the height and accordingly change the outlet flow rate. So, if we have implemented a feedback control system, then your output will be a function of height. So, this is your equation number 2. So, if I write the degree of freedom again, so now I have still the same number of variables 3, but then I have 2 equations. So, the degree of freedom is 1. So, by implementing one control loop, I have reduced the degree of freedom by 1. So, every process control loop will reduce the degree of freedom by 1. So, that automatically tells me how many maximum number of control objectives I can satisfy in a process. So, the maximum control objectives which can be satisfied in a process will be equal to the degree of freedom. So, if we look at the previous example, we had 2 degrees of freedom, which means any 2 of F in, F out and H can be specified. So, now here the disturbance F in, even though I am calling it as something which we can manipulate, we know from the typical analysis for these kind of systems that even though I am calling F in as a variable, there is very little capability we have in terms of manipulating it. So, we would typically not consider it to be something which we can vary. So, the degree of freedom automatically gets reduced by 1 because there is no freedom on choosing F in. So, there is a degree of freedom of this system is 1 and practical degree of freedom is 1, and therefore, only one control loop, which is the controlling height, would just make the system completely deterministic, and then that is the only control objective, or only a single control loop can be implemented on this particular system. So, to summarize this second part of the first week's lecture, we have seen that dynamic models are required for efficient process control, because they will give us the way of how system behaves, on which can be later on leveraged to design a control strategy. And depending on the type of system for which we want to write the dynamic model, any one of first principle or white box model, empirical or black box model, grey box model. So, these are the three different ways in which the dynamic model can be formulated, and depending on the system complexity, one model may be better than the other. We typically represent all this dynamic model into Laplace domain, because it gives you it simplifies the analysis as well as controller design. And then lastly, degree of freedom analysis is typically carried out before starting any control work, because that gives you an upper limit on how many control objectives which can be satisfied for that particular process. Thank you.